So today we'll be talking about capacitors. Now, what is a capacitor? Well, we usually have two metal plates that are some distance d away from each other, and they each have a surface area, which we'll call A. And in between, we have either air or some other kind of material. Now, what a capacitor does is that it's going to store charge. So this might be positively charged here and negatively charged here, and we find that there is going to be a difference in voltage from one plate to the next. We also find that there will be an electric field. Now, what a capacitor does, it's going to store this charge. And the difference from one capacitor to the next is a property called its capacitance, where we define capacitance to be epsilon, which is a property of what's in between. In the case of air, epsilon becomes epsilon naught times the surface area divided by the distance between the two plates. And this capacitance is a property of how much charge it can hold per unit voltage. So we have that this is equal to Q, where we say Q is the total amount of charge that our capacitor can hold divided by the change in voltage. We can also write this to be that the total Q is equal to C times V. So we can see that if we increase the capacitance, then we can increase the amount of charge that our capacitor can hold. Likewise, if we increase the voltage, which is to say the difference in potential, in electric potential from one plate to the next, then we can also increase our charge. Now, what happens when we have capacitors in parallel? So we have something that looks like this. And this might be a battery, for example, positive, negative. So for our capacitors, what we find is that they have the same difference in voltage. So from here to here, we have the same V as this side. However, we have different capacitances for each of the capacitors. Now, what would happen if we wanted to try and express this in terms of a single capacitor with some capacitance C? Well, one thing to note is that, once again, the C capacitor has the same difference in electric potential as these two capacitors. Now, in addition, we find that the Q that is stored by C1, which we'll call Q1, and the Q that is stored from C2, which we'll call Q2, must be equal to the total amount of charge that is amassed by our single capacitor, which we'll call Q. So we find that Q, the total charge, must equal to the charge held by the first capacitor plus the charge held by the second capacitor. And since we have this relationship, then we can simply plug in to find that C times V is going to equal to C1 times V1, which is just V, plus C2 times V2, which is also just V. And since we have a V common to all terms on both sides, we find that for capacitors in parallel, which is to say that their voltage here will be the same. For capacitors in parallel, we have that C is equal to C1 plus C2. So if we have two capacitors in parallel, then if we wanted to turn it to only one capacitor, we would need a capacitance of the sum of the two original capacitances. And if we had three capacitors, we would sum all of those three up if they were all in parallel, and so on and so on. So this is for capacitors in parallel.